Assalamualaikum and greeting to my lecturer, Dr. Syed Hakim and fellow friends. In this video, I will explain about laboratory force in a statically determinate cantilever truss. My name is Nurliana binti Azhurin. My metric number is AF220054 and I am from group 5. This is the fellow members in this group. The objective of this lab is to examine a statically determinate frame and to analyze the frame using simply pin joint theory. The learning outcome from this lab is the application of the engineering knowledge in practical application to enhance technical competency in structural engineering through laboratory application, to communicate effectively in group, and to identify problem solving and finding out appropriate solution through laboratory application. The theory used in this lab is a truss is a structure composed of slender members joined together at their ends points to form one or more triangles. The joint connections are considered as pin joint without friction. In order to determine the forces developed in the individual members at the truss, there are two assumptions should be made, which is the members are connected to each other at their ends by frictionless pins. That is only a force and no moment can be transferred from one member to another. The second assumption is external loads are applied to the truss only at its joints. This is the material and equipment used for this lab. The procedure for this lab is: first, unscrew the thumb wheel on the redundant member. Note that it is effectively no longer part of the structure as the idealized diagram illustrates. Second, apply the preload of 100 Newton downward, re-zero the load cell, and carefully apply a load of 250 Newton and check that the frame is stable and secure. The third, return the load to zero, recheck and re-zero the digital indicator. Never apply loads greater than those specified on the equipment. Last one is apply load in the increment shown in table 1, recording the strain readings and the digital indicator readings. Complete table 2 by subtracting the initial 0 strain readings. Be careful with your sign. This is our result obtained for table 1 and table 2. For the first graph, we choose value member 2. For the second graph, we choose value for member 7. And for the last graph is graph of deflection against load. To get the results for table 3, we use equation F equal to E strain A for experimental force and method of joint for theoretical force. For discussion, for first question, from the experimental results, we obtain that member of cantilever 4 has the highest force, which is negative 439.32 Newton, and for theoretical force is negative 500 Newton, which means it is not a big difference with experimental results. For second question, from our theoretical calculations, we found that member 2, 3, 4 and 8 having compression because the negative sign, while member 1 and 7 having tension because the positive sign. For the third question, the reason of member 5 having the readings which is almost 0 is because the load distribution in member 5 is minimal or no load. If truss is symmetric or exhibits redundancy, member 5 may not experience significant forces. For question 4, strain gauge can be effective transducer for measuring forces in a framework. Strain gauge measure the deformation or strain of an object. When forces applied to a structure, it deforms and the strain gauge can detect the deformation. For the last question, the concept of pin joint theory assumes that joints in framework are frictionless and allow only two force components, which is tension or compression along the member. Framework can still be analyzed using pin joint theory as an approximation, especially if deviations from ideal conditions are small or negligible. In conclusion, the analysis force in a statically determinate cantilever truss in the laboratory reinforces key engineering principles. Understanding the distribution of forces is crucial for designing structurally sound systems and the practical application of this concept enhance our ability to create resilient and efficient structures. That's all for this laboratory video. Thank you.
Assalamualaikum and greetings to Dr. Said and my fellow friends. I'm from Group 5. My name is Nur Awada binti Abdul Latif, measuring number CF220125. I will present the experiment for bending moment in the beam. For introduction, bending moment is similar to the force, causing a beam to bend under a load. Think of a diving board. When someone stands on it, the board bends. Bending moment measures this bending force at different points along the beam. In designing structures like bridges, buildings, it ensures that it can withstand weight and force without breaking. Engineers use knowledge of bending moments to create structures that are both strong and safe. For objective, to examine how bending moment varies with an increasing point load and how bending moment varies at the cut position of the beam for various loading conditions. For the experimental procedure, first we calibrate the digital force display meter to 0, and second we hang a 100-gram mass to the left of the cut, and then we record the digital force display as the readings at table 1, and then we repeat with masses from range 200 to 500 gram while noting the readings. For the calculation part, below you can see there's two formula, which is the load formula is by converting mass to force, which is in Newton unit. Each trial convert the mass applied to the left of the cut into force in Newton by multiplying it by the acceleration due to gravity, approximately 9.81 meter per second square. This provides the applied force in Newton. The second formula, which is the bending moment in Newton meter unit, is to converting the digital force display readings to bending moment by multiplying each display force reading by 0.125 to determine the bending moment at the cut in Newton meters. To find the theoretical calculation of bending moment, as you can see a figure above with the formula of moment at the cut section, which is MC equal to W, the weight in Newton, and A indicates as the length of span from reaction A to the cut section, and L indicates as the full length span of the of the span, which is 440 millimeter. For the methodology, there's three cases we do the experiment, as shown as example from figure 2, 3, and 4. For data and results, there's two tables, which is table 1 to answer the part 1 and table 2 for part 2. These are the value that we obtained by calculating using the formula, and also the data we obtained during the experiment, such as after putting the weight, which is load in Newton, and the force will be showed from the display meter. For discussion and conclusion, to answer the part 1, which is question number 1, derive equation 1. I derive it in this method, and to answer the question number 2, there's two graph, which is graph number 1, force versus the experimental bending moment, and graph number 2, the force versus theoretical bending moment. There's not much different. As you can see, the number was increasing and differs only a little value. To answer the question number 3, the graph reveals a linear relationship demonstrating that bending moment increases proportionally with added loads. This fundamental connection between bending moment and applied load is observed as the moment equals the product of applied load and distance. The observed values closely align with experimental results. To answer the question number 4, the graph indicates that the inaccuracy of 0.0595 Newton meter for the theoretical and experimental values utilized in our equation differs little from the rest. Below you can see the theoretical bending moment method by using the formula given. To answer the question for part 2, question number 1, in 3 cases, the experimental and theoretical results varied by an amount less than 0.001. The inaccuracies between the experimental and theoretical outcomes could be a result of random errors. Errors in the data, measurement techniques during the operation of bending moment machines may arise from the approach taken by the students. For the question number 2, to maintain the equilibrium, it is essential that the forces and moments on both sides of the section counterbalance each other. This ensures a consistent bending moment regardless of the chosen side of the section. This principle is fundamental in the analysis of structures and materials under load, where equilibrium conditions are crucial for the stability and accurate calculation. To answer the question number 3, plot the moment force diagram for load cases in figure 2, 3, and 4. As you can see from the figure above, these are the shape of our figure and the value that we obtain by calculating the maximum and the minimum value. For question number 4, the graph shows negative bending for case 1 and positive bending for case 2 and 3. Negative values indicate concave downward bending when the downward load exceeds the upward load. Conversely, positive values indicate convex upward bending when the upward load surpasses the downward load. That's all from me. Thank you.
The objective of this lab is to determine the relationship between span and deflection. It is crucial for a beam to exhibit ample stiffness to prevent detrimental impacts on neighboring structural elements due to excessive deflections. Often, building codes outline maximum permissible deflections, especially in relation to the beam's dimensions, particularly its span. To avoid permanent distortion, the beam's actual deflection must stay within the elastic range. Therefore, when assessing beam deflections under load, elastic theory is employed. In this experiment, the complete deflected shape of the beam is determined using the double integration method. The theory of this lab is the double integration method is used to calculate the deflection of a beam under a given load. The basic idea is to integrate the equation of the beam's shape twice. Firstly, start with the equation for the elastic curve. Secondly, integrate the equation twice to find the shape of the beam. Thirdly, determine the bending moment using loading and support conditions. Fourthly, substitute bending moment into the integrated equation to find the deflection. Lastly, in a lab, measure deflections under known loads and compare with theoretical predictions. By comparing theory with experiment, the double integration method's accuracy and the beam's behavior can be assessed. The apparatus were used in this lab were specimen beam, which used aluminium, digital dye-test indicator, hanger, and lasers. The procedures of this lab is firstly the movable knife edge supports were positioned 400 mm apart. The chosen beam was placed on the supports. At mid-span, the hanger and the digital dye-test indicator were positioned and the digital reading was 0. Then an incremental load was applied and the deflection for each increment was recorded in the table. Lastly, the above steps were repeated using spans of 300 mm and 500 mm. For result and discussions, in a span deflection lab with T-frame loads 0.981 Newton, 1.962 Newton and 2.943 Newton and varying spans 500 mm, 400 mm and 300 mm, 3 experiments were conducted. The results showed discrepancies between experimental and theoretical values. In experiment 1 with a 500 mm span, The first load experimental result is 25% lower than theoretical. In second load, experimental result is 60.54% difference, and the third load experimental result is 13.16% lower than theoretical. In experiment 2 with 400 millimeters span, the first load we obtained 38.46% lower than theoretical. In second load, we achieved 50%, and the last one is 42.24% lower than theoretical. In experiment 3 with a 300 millimeter span, the first load is 31.25% lower than theoretical. For the second load, experimental result is 42.42% lower than theoretical, and lastly, experimental result for the third load is 55.1% lower than theoretical. The percentage differences vary, suggesting inconsistency in the experimental results. The consistent trend might indicate systematic errors or inaccuracies in the experimental setup or measurements. In summary, our beam deflection experiment showed difference between expected theoretical outcomes and actual results. This variation highlights challenges in our experimental setup, including measurement inaccuracies and other factors. The occurrence of negative theoretical deflection values indicates tension in our experiment. Despite these challenges, the experiment offered insights into how the span responds to different loads before reaching a failure point. The data obtained can be used to design a safety factor, contributing practical knowledge to structural considerations. To enhance future experiments, it's recommended to analyze sources of error, refine the experimental design, and validate the theoretical model. While our experiment may not have been perfect, it has advanced our understanding of structural behavior, emphasizing the ongoing process of improvement in experimental methods and theoretical models.
Hi, Assalamualaikum. My name is Muhammad Faizal Mr. Faisal. My matrix number is CF 220039. I will present about a part of mechanic of material experiment, which is shear force in a beam. So first of all, introduction. When a beam is loaded, the forces cause the beam to bend and to undergo a vertical displacement, elastic deformation. These effects are due to vertical component of forces acting perpendicular to the longitudinal axis of the beam. The vertical displacement tend to shear of beam. Shear means relative movement between two parts of a structural member. Any beam must be designed in such a way that it can resist shear. The purpose of this lab is to demonstrate the principle involved when determining shear force in a beam. Second, objective. First, to examine how shear force varies with an increasing point load. Second, to examine how shear force varies at the cut position of the beam for various loading condition. This is a formula that we use to calculate shear force. First, equation 1, W times length minus A divided by length. Second equation, shear force at the right of the cut section, negative W, which is load, times A divided by L. Second, the shear force at the cut is equal to the algebraic sum of the force acting to the left or right of the cut. For procedure, part 1, check the digital force display meter, it's 0 with no load. Second, place a hanger with 100 gram mass to the left of the cut. Third, record the digital force display reading in the table 1. Shear force at the cut equal display force. Repeat using any masses between 200 gram and 500 gram. Convert the mass into a load in Newton, multiply by 9.81. Final and last one, calculate the theoretical shear force at the cut and complete table 1. For part 2, first, check the digital force, display meter 0 with no load. Second, carefully load the beam with the hanger in any position and load as example in figure 2, figure 3 and figure 4 and complete the table 2. Third, record the digital force display reading where shear force at the cut is equal display forces. And last one, calculate the support reaction RA and RB and calculate the theoretical shear force at the cut. This is our instrument to do the shear force in a beam experiment. This is our data. The data are experiment shear force and theoretical shear force are not big differences, which is 0.3 and 0.357, 0.7 and 0.713. And for table 2, also no big differences between experimental shear force and theoretical. From the graph, we noticed that when the load applied on the beam was increased, the shear force will also increase. However, the experimental portion, the graph is not 100% linear. This could be due to the sources of error when recording the forces measurements or calibration the equipment. This is our sample calculation. Let 1 part 1 to get the load in Newton. Second, shear force at the cut. And then our calculation for shear force at the cut proof. So figure 2, figure 3 and figure 4. This calculation for to prove the left forces is equal to the right forces. This is our shear force diagram and the calculations for figure 1, for figure 2, figure 3 and figure 4. So the conclusion from this experiment, we are able to determine how shear force varies with an increasing point load. It was also seen how shear force varies at the cut position of the beam for various loading conditions. From this lab experiment, it can be concluded that when the load we place at the beam is increasing, the shear force will also increase. As well, it was proved that the shear force at the cut section is equal to the forces acting both right and the left side of the cut section of the beam.
Hi, my name is Muhammad Karunazan bin Jamaluddin. My metric number is CF220003. Okay, today I want to present about buckling of strap. Okay, objective of the lab is first to examine how shear force varies with an increasing point load. Second, to examine how shear force varies at the cut position of the beam for various loading conditions. Introduction. A comprehensive member can fail in two ways. The first is via rupture due to the direct stress, and the second is by an elastic mode of failure called buckling. Short wide compressive member tends to fail by material crushing. Okay. Second, when buckling occurs, the strap will no longer carry any more load, and it will simply continue to buckle. Stiffness can then become zero, and it useless as a structure member. Okay. For the apparatus, first we use the buckling of strap apparatus. Second, we use the aluminum strap, which is for the length we use is 320 mm. Second, 370 mm, and third 420 mm. Then we use the top pin. Okay, result. For pin, the length of 320 mm. For buckling load experiment, we got in negative 108, and for the buckling load theory, we got is 61.39, Okay, for the length is 370 mm. For the bucking load experiment, we got negative 28, and bucking load theory we got 45.92. So the length for 420 mm. For bucking load experiment we got negative 22, and bucking load theory we got 39.63. Okay, for feet spin, for the length 320. For bucking load we got negative 194, and for the length of 320 mm we got for the bucking load negative 104, and for the length of 420 mm we for the bucking load we got a negative 71. Okay, for feet the length of 320 mm the bucking load we got is negative 339. For the length of 370 the bucking load we got a negative 124, and the length for 420 mm the bucking load is negative 74. Okay, calculation for young modulus in the experiment we use is 69 times 10 the power of 9 Newton meter cube, and for the moment area is 9.23 times 10 power of negative 12 meter of power of 4, and cross section area is we use 3.42 times 10 the power of negative 5, and radius of variation is 5.2 times 10 power of negative 4, and we use the buckling formula to get the data for pin, feet spin, and feet fits. Okay, calculation for pin for the length of 320 mm we got is 61 and 39 Newton. For the length of 370 mm we got 45.92 Newton, and for the 420 we got a 39.63 Newton. Okay, for feet spin we got 122.764 Newton, and for the length of 370 mm we got 91.82 Newton, and for the length for 420 mm we got is 71.26 Newton. For fits the length of 320 mm we got 245.53 Newton, and for length 370 mm we got 183.65 Newton, and for the length 420 mm we got 142.53 Newton. So this is our graph for the experiment. The first is graph bucking load experiment versus 1 over L cube meter, and the second graph is graph bucking load theory versus 1 over L cube meter. Okay, so based on the graph that we plot, the difference to the end of the pin for the result of gradient experiment is 13.51, and the slope for the theoretical calculation result of 6.28. Different to the feet spin of the gradient experiment result was 30, and the gradient theory result for the calculation is 12.56. In addition, the difference for fit fits and condition for the gradient experiment result are 64.63, and theoretical calculation the result is for the slope is 25.12. This experiment result show that the slope is greater than the slope for the calculation result. In practice, the buckling of the experiment is higher than theoretical. Okay, for question 4, because the ratio of the bucking load Newton to the 1 over L cube remain consistent through the graph. The Euler formula can reliable forecast the buckling load. It also shows that the buckling load is inversely related to the length. Therefore, when the length is 0, the buckling load should be 0. Okay, part 2. The comparison between experiment and theoretical ratio by and condition. Okay, experiment gradient, pin. 13.51 for fixed pin is 30 and fixed width is 64.63. For experiment ratio is we got is 1 for fixed pin with 2.22 and for fixed width is for 4.78. For ratio for the theoretical ratio, for pin we got 1 and for fixed pin we got 2 and for fixed width we got 4. So comment on the experiment and theoretical ratio. Since the experiment ratio in the table does not match the connection and use, we may refer that according to the theoretical ratio value, the fixed end is substantially stronger than the pin end. This demonstration that contract to a pin connection, greater force should be applied to the member of the joint fixed end. The ratio is twice great as the pin instant when one of the end is changed for pin end to fixed end. The same thing happened when both ends were changed to fixed end. The experiment ratio does not match the theoretical ratio due to a number of mistakes made during the experiment, including improperly tightening the screw and improperly tightening the sliding crosset. For the conclusion from the experiment, based on the buckling of such experiment, we can conclude that the fixed end is much stronger than the pin end, and that's the member of the joint fixed end connection should be adjusted to greater force. However, in terms of other criteria, the pin end is used for steel connection because the fixed end connection are typically permanent. Steel always use bolt and nuts rather than fabrication connection. Okay, conclusion. We can conclude from the buckling of such experiment that fixed end are very much stronger than pin end, and that's the member of the joint fixed end connection should be subjected to greater force. However, other criteria typically apply to concrete beam or column connection when using fixed end connection, because a fixed end connection is often employed for a permanent connection. The pin end is utilized for steel connection.